So thanks for the very nice introduction. And yes, I'm going to share some parts of the dissertation on demand management in shared mobility systems, which I submitted and defended successfully last year. As you have heard, a lot of this work was motivated from practice. So I closely collaborated with GERAD, which is, as you already know, Europe's largest free-floating car sharing provider. And if you don't know how free-floating car sharing works, no problem, because the...
Is it not working? Yeah.
Because the principle is very simple. So you just open the mobile application of the provider. You look for a vehicle, like for a car in this case, in your neighborhood. And then if you decide to book it, you just book it and can drop off anywhere within some operating area. So even though like this work is strongly motivated from car sharing, it applies to different shared mobility systems. So why is that? Well, from a provider's point of view, what you do actually is you offer a fleet of vehicles to the customers. And these vehicles can be cars, but also maybe bikes or scooters. And then the customers spontaneously rent these vehicles, right? So from the provider point of view, when we're talking about pricing and availability control, it really does not make a difference if you are managing cars or bikes. So this is why I'm talking about shared mobility systems in the general term. Let's look at some background really quickly. So the origins of shared mobility systems are surprisingly early. So like in the 1950s, these kind of systems have been tried to put into place the first time. It grew very quickly, and what's especially growing very quickly are the free-floating shared mobility systems. So in a free-floating shared mobility system, in comparison to a station-based system, the operator defines some area in which you can pick up and drop off the vehicles spontaneously. Whereas in contrast for the station-based systems, you have to return the vehicle or pick up the vehicle and return it at some predefined station. So this here gives you a lot more flexibility. And I think, if I'm not mistaken, like the Commune Auto offer, which is also a car sharing operator here in Montreal, is offering actually both. So they have like the station-based variant and the flex variant, which is that doesn't. In the literature, a lot of colleagues, so to say, have dealt with different optimization problems in the context of shared mobility systems on all levels of decision making from like strategic questions to more operational ones. And from the provider's point of view, the biggest challenge to operate such a system profitably is that you have a dynamic imbalance between supply and demand. So what is meant by that? Well, as you can imagine, you have demand patterns which vary throughout the day. And this, especially for the free-floating shared mobility system, leads to the situation that vehicles quite often do not stand available where you need them to serve the future demand. So there's a mismatch between supply and demand. And what literature has focused on, like traditionally, is supply-sided approaches, in particular vehicle relocation. So what they do is to bring one car from one location to another, such that supply and demand are balanced. So this works in principle, but it is quite costly, as you can imagine, especially for car sharing. You need a lot of personnel to transfer one vehicle to another location. And also, like from a, let's say, sustainability point of view, you actually, as a maybe also as a city or as like some region, what you want to do is to reduce the traffic with these kind of new mobility offers, but you don't want to increase that with these relocations. So I think hopefully I convinced you that there are good reasons to look for some alternatives. And one alternative is what I considered and proposed in my dissertation, and it's using demand management. Demand management is a term coming from the literature on pricing and revenue management, where the idea is that you impact the system not on the supply side, but on the demand side, and in particular, use pricing algorithms to do so. So the theoretical advantage is that when you set prices, differently. This does not come with any direct costs to you as a provider, whereas you have costs, relocation costs, when you perform these relocations. But the problem is, of course, that your impact, your influence on the system is not as direct. If you perform a relocation, you know exactly where the car will be placed. So you have like a deterministic state transition. But when you set different prices, it has an effect on the customer behavior and then in the long run on the system, but the impact is more implicit. So the key thing you have to make sure of is that you model the response of your customers to your prices accurately and endogenously in your models, and that you also keep track of what we call the network effects, so that you foresee what's going to happen with your supply and your demand in the future. So as promised, I will focus on one particular pricing problem here in this talk, and going to explain what's behind the pricing at ShareNow. There are different pricing problems and problems in the context of demand management, shareability system, but here we will focus on what's behind all that. So what's the algorithm which later was put into practice at ShareNow? The first thing which you have to realize or understand is that the car sharing provider discretizes the operating area into the different zones, and the course of the day or the considered time frame is discretized into multiple units. And now what the task here was for us was to come up with minute prices that are valid for a particular combination of zone and period, such that later you could visualize the prices here in a table. So we denote this problem as the origin-based differentiated pricing problem. What does it mean? Well, origin-based prices means that the price which is valid for your rental really only depends on the spatial temporal origin of your rental. So where and when do you start? Doesn't matter where you go. This, for example, if you take this additionally into consideration, would be some kind of trip-based pricing where spatial temporal origin and destination both impact the price. But this is actually proposed about in literature, but not very practically implementable. Also, it's a differentiated or static pricing, which means that prices are pre-computed. This also has some practical motivation. You want to have this table in the end, which you upload in your backend, and then a vehicle would check, so to say, okay, I'm currently in this zone, I'm in this period, so I cost this specific minute price, right? So it is an approach which allows you to pre-compute the prices. It's not, I will talk about that later for some other paper or problem which I consider. It's not a dynamic pricing in the sense that you recompute prices at every instant. Instead, what you do is you pre-compute everything. So I think I've forgotten to say this. So prices have to come from a predefined set of discrete price points. Also, the practical reason is that you as a provider, when this was first put into practice, no customers knew about like changing prices. So the provider was kind of afraid of like this shitstorm. Oh my God, prices are changing now suddenly. So at least you want to have some kinds of consistency and don't vary your prices. So how do we get this table here? How do we get the prices which at the end maximize the profit, or more specifically the contribution margin, which is generated from the rentals that we realize? The approach here is based on mixed integer programming, and more specifically, we modeled this problem based on a deterministic network flow formulation. The idea is that every node in this network here represents one combination of the zone and period. And the vehicle movements in the system now are modeled as flows within this network. So for example, you have rentals from one location to another location. You can also have idling vehicles. And then of course the vehicles will stand available in the next period in the same zone or at the same location. The entire optimization model looks like this. Of course, I'm not going to go into detail here. I just want to give you an idea like what the components are. So the objective function maximizes the profit or the contribution margin Here, it comes into play which rentals realize, which prices were set, the rental durations, and also the minute prices that you face as a provider. Then we have a set of constraints which models the conservation of flow. So as you can imagine, all vehicles which arrive in one of these spatial temporal nodes also have to leave there, right? So either they stand idle or they are going to be moved by the customers. These constraints then make sure that the model cannot freely decide where the vehicles pop up. And also these constraints ensure that in the beginning of the considered time frame, you have vehicle distribution as you realize, or as you can observe it in the instant data on average. Now, then we have constraints which make sure that exactly one of the discrete price points is chosen for each node here, for each combination of zone and time. And then we have a bunch of constraints which model how rentals realize. And here I need some more time to explain that. So these constraints also model some further characteristics of our origin-based differentiated pricing problem. First, it's a pure pricing control. So what does it mean? Pure pricing means that the provider sets prices and everything follows from there. In particular, the provider is not allowed to prevent any rentals which could happen. I'll give you an example. So let's consider this node here. And let's say you set a certain price, which induces some demand level. Now you have, let's say, fewer available vehicles. The constraints now ensure that the minimum of the two values, so in this case, the supply, is actually the amount or the value of rentals which realize, right? So it's the minimum of two, but note that it's not that this minimum is not an upper bound on the rentals. If it was an upper bound, the model could decide to only realize fewer rentals, which could actually be better for the system overall in the long run. But this is not what's happening in practice. If you have vehicles available and you have customers coming, these vehicles will be taken, right? So since the provider has only the possibility to set prices and cannot prevent any rentals, we call that pure pricing control, and this is ensured by these constraints. So now we know how many rentals realize in a certain zone period combinations. The question then still is, where do these rentals go? And note that this is a deterministic formulation here, and we are modeling and predicting, or the model predicts what's going to happen on average on a typical weekday, let's say. This is also why the decision variables here, like the rentals and the idling vehicles, they are not integer variables, but continuous variables. So the rentals which realize can split up or do split up in proportion to the demand. So if you have a lot of demand, let's say in this, from this zone to this zone, also in the model, you will see more rentals going from this zone to this zone than to another zone, for example, right? So you could think of like a first come, first serve procedure here, which is modeled in a deterministic fashion. So it turns out that this problem is an NP-hard problem. So we need to come up with a solution algorithm which actually scales to real life sizes. Because remember, at the end, we want to apply it to Chernoff practice. And this solution approach, which we developed for the problem, is based on approximate dynamic programming. You might know ADP as a solution method for stochastic dynamic problems, but it can actually also, like in this case, be used as a decomposition approach for solving deterministic sequential problems. And the idea is as follows. So instead of solving the entire problem over all periods in an integrated manner, you solve iteratively multiple subproblems. And each subproblem consists of two parts. In the first part, the subset of the periods, which is called here the horizon, is considered explicitly. which means that all the constraints and the optimization and the objective function is modeled one-to-one as in the original problem over this horizon. The second part, however, is only considered implicitly. And this means that, or what you do actually is that you insert a function in the objective of the subproblem, and this function approximates the value to go from the end of the horizon to the end of the original time period. And if you are capable of finding good approximations here of this objective value to come, or this value to come, it allows you, this is the whole idea, to solve multiple, a lot smaller problems, which then become tractable without forgetting, so to say, that different vehicle distributions have a different value. Because you can imagine that if you put all your vehicles in one zone, this will not be as good as having them nicely distributed, especially with regard to the different demand levels which you have in different zones. So again, the idea is multiple subproblems, and in each subproblem you insert a function which links the vehicle distribution at the end of the horizon to the value to come until the end of the overall time frame. The question then still is, how do we come up with these value functions? In this case, it turned out what works quite well is a piecewise linear function, which is a function of the available vehicles here. And we believe this is for two reasons. Like for the one reason is that the linearity of the objective and the model is retained. And the other thing is that it allows to model decreasing marginal values of vehicles. So what does that mean? Well, if you put a vehicle in one of the zones, this gives you some value. The second vehicle which you will put in this zone will not have a higher marginal value because you have some demand saturation at some point. So this kind of curve here can be modeled with or replicated with a piecewise linear function. So the results, very quickly, like from our numerical analysis, showed that this approach works quite well and increases the objective, so the contribution margin in the range of 5 to 15% with regard to the former pricing, which was put in place at GERAD. It also beats several benchmarks, in particular like a myopic optimization, where you optimize prices for every zone period combination, but where you do not consider what's going to happen in the future. And the results also show that a considerable portion of this increase can actually be explained by using the value function approximation. So yeah, it's not only say like nice formulas, but there's also some value inside. What does that all mean for practice? Well, as you can imagine, practitioners are not very keen on sharing so much data is in terms of profitability. But what I can share with you is GERAD implemented this algorithm, or we supported them in implementing this algorithm at the end of 2018. They call it flex pricing. Yeah, okay. So I mean, origin-based differentiated pricing, maybe not as handy as flex pricing. I see that. And yeah, maybe some small anecdote, even though I'm risking to run out of time. So sorry? Yeah, okay. So at the time when we were supporting GERAD to calculate all these pricing tables for different cities. We started, I think, in Florence with Italy, but then also Munich. So after that was rolled out and put into place, I realized that the area where I was living in Munich, prices were a lot higher than before, right? So maybe I should have implemented another constraint and sneak it in, but I didn't foresee that. Okay, so under this roof, demand management checkability systems, in my dissertation, looked at specific optimization problems, like the one I shared with you already, differentiated pricing on a zone level, but also some other optimization problems, which I quickly summarize on the next slide, and also some more fundamental work, which was especially necessary to model free-floating shared mobility systems accurately. So we've seen this pricing on an aggregate level, meaning on zone and period level. And in the second project, what we did, we went on a disaggregate level, meaning that you optimize prices for every customer individually and also in a dynamic fashion. So the idea is someone opens the application, you check which vehicles are within the walking distance, because you as a customer would not walk anywhere in the city, but only maybe a kilometer or something. And then the algorithm optimizes in real time the prices for this particular situation. This modeling is based on Markov decision process, and it also uses approximate dynamic programming in its traditional manner, I would say, using, in this case, non-parametric value function approximation to assign values to the different vehicles, because you also want to foresee in the future, if a customer takes this vehicle, how much is the system going to be worth in the long run? And the nice thing about going down to this disaggregate level is that you can model the customer choice behavior much more accurately. There are, for example, discrete choice models like the multinomial logit, which we use, which allows to, after training with real life data, allows us to incorporate in the optimization that it's actually a lot, like for a customer, it's the walking distance has a high impact on his or her utility, right? Customers are kind of lazy and they prefer actually the more expensive vehicle, which is closer to them than the other way around. Well, there are different customer segments, but that was like a general finding also. In this problem here, we considered that shared mobility systems, like shared mobility system providers like ShareNow, started to offer also pre-booking. So the idea here is that you can, as a customer, decide tomorrow at that time, I want to have a vehicle available at a certain location. What you now have to do as a provider, if you accept this, is to either relocate a vehicle to this particular place. This comes with some relocation costs. What you can also do instead is to block a vehicle which already stands available at the correct location beforehand. But if you now just start blocking all the vehicles, of course, you will lose some revenue. So you have opportunity costs. In finding a good balance between these opportunity costs and these relocation costs is what this paper is about. And here we are also in the dynamic stochastic world using Markov decision processes and so on. And the last paper or project I was working on, as I said, was a more fundamental about modeling. Earlier, I tried to explain how the model in this first project models how many rentals realize in one zone period combination. And I said, okay, it's the minimum of supply and demand, which is the amount of rentals realized. However, this only holds under certain, let's say, conditions. In a general case, if you imagine that the zone is quite large, maybe several square kilometers, and you have one blue vehicle available in that zone, you cannot be sure that if you have one customer, the red dot, arriving with a certain willingness to walk, you cannot be sure that they actually match, right? So more generally speaking, what these matching functions do is they take these spatial characteristics of zones and also the limited walking distance of customers into account to predict on average or like in expectation how many rentals realize. And this allows you to model free-floating shared mobility systems much more accurately, and we could show that it also results into better pricing decisions at the end. So what happened to all of these papers? 3 of them so far got accepted, which of course is really nice. 1 was rejected, which is not very nice, so it's back on my desk, and I have to find some time to do that. What am I working on now? This is my last slide, I promise. So I try to strike a balance between exploitation and exploration. So as I said, I still need to finish some work back from my dissertation. I started to collaborating with the University of Porto, but in the same field, as we see in practice, car rental and car sharing, which formerly also in the literature have been considered as totally different problems, actually are not that different anymore, because you also see providers like Sixt, which who is offering both Sixt share and Sixt car rental. So the question, or there are a lot of interesting questions related to the to operating these kind of systems here. And yeah, I did some work on scheduling, which was not too exciting in my point of view, but some or two projects of which I'm like really excited about currently is this one here. There I worked back with colleagues back in Germany on a particular pricing problem. Probably you're all aware with the reinforcement learning setup, where an agent interacts with some environment. We argue that you cannot use reinforcement learning directly for pricing approaches because it would require you to set prices in the real world. And because the algorithm also strikes a balance between exploitation and exploration and has to find out which prices actually are bad, this is quite costly. So what offline reinforcement learning instead does is to use your past, let's say, booking data and the past prices that you have set, and you try to find a pricing policy which is better than the behavior policy with which your data was generated. So you don't have any way to interact with the system, and the hope, so to say, is that you get a better policy just from learning from the past data. And then the last project, last but not least, this is with colleagues from here, with Alexandre and Thibault. We are building on work which Thibault already did on making certain machine learning predictors more interpretable by using optimal counterfactual explanations. This existing work was considering classification problems, and now we extend this to regression problems. And with that, I thank you for your attention.